And it has an index of refraction of NC. I don't like that because core and cladding both have a C subscript, but the way you can always tell, the lesser of the two is the cladding. That's the simple way to get it. The core has a higher index of refraction. In general, the index of refraction is equal to the square root of epsilon relative. Remember that always. Now, when we take a look at this is called a stepped index fiber, and I hope you had time to look at this. What it means is you have a clear core that has a given index of refraction, you have clear cladding like that. This is called stepped index, just for the record. That's the most, as far as I know, the most common kind of fiber. For this type of fiber, there's two things of importance. This is the main one. You'd like to know what frequency of light or wavelength of light, and these are optical light. They're not megahertz or gigahertz. This is optical frequency, 10 to the 14th kind of hertz, all right? So optical wavelengths, visible light, and it can be infrared and micro, it can go above that to ultraviolet, but in general, it's something very high frequency. Think of optical packets, all right, where you're talking about the amount of photons actually per meter squared rather than the actual power density in watts per meter squared. This is important. When you talk about this, to get a single mode, only one mode, is that's what you would want, because that means that all the energy that's flowing is moving at the same velocity. There's little dispersion. So this is what you want. For one mode only, this is the condition. Now A is the radius. I didn't put that here, but this would be A. It's the radius of the inner core for the fiber. Now this is the equation for it. I'm going to explain something about this equation in a second. If you look at this equation right here, lambda naught, since that's free, the naught means free space lambda, that's C over F. Okay? But usually when we take a look at optical stuff, we're always talking about lambda in terms of wavelengths. How many have seen, when you had optics and physics, they didn't talk about frequency, they talked about the wavelength, right? You went from infrared for visible up to the dark, or the light, dark blue actually, and into the ultraviolet, right? From red, very dark red, and it's roughly 400 to what, 700 nanometers, I think? About, I don't remember exactly. That's the type of thing you're talking about. This is what this is in frequency, this is free space wavelength. That's the equation that gives you single mode. Actually, what it should be, I put an equal to it for a single mode, but this would be the wavelength. Now, usually what's done, if you listen to me for a second, usually we know the fiber's value of its index of refraction. That's a number we have. Could be 1.18, 1.15, and we know the claddings could be 1.05, 1.11, something like that. So we know these are givens. We know K01 is a Bessel number that has to do with the solution of Bessel's equation. I try to give you a little insight in Bessel equations. And when you do the del squared operator, del squared V minus K, or plus K squared, or plus beta squared times E equals 0. In cylindrical coordinates, when you separate out variables, the variable that's actually in the radial direction is a Bessel equation. The solutions to that are not sines and cosines or exponential. They're called Bessel functions, so the first kind, second kind, things like that. Did y'all take a look at that? At least expose yourself to the terminology. Now, Bessel functions have zeros. Just like when I have a sine of x, the zeros of that are sine of 0, sine of what? Pi, sine of 2 pi, right? Those are the points where the sign goes to 0 when the argument is at those zeros, right? The Bessel function has a 0 at 2.405, and I try to show that. That's the Bessel function, and it's of order 0, and it's also the general solution to the wave behavior inside a waveguide in the first mode. I mean, the O mode it's called. So just accept it, don't worry about it. Now, what does it really mean when you do this? Well, what happens is I got all this stuff over here. I got NF, got NC, got K0, and I also have the wavelength of the optical laser I'm going to use to excite it. Y'all with me on that? And that's lambda naught. I know that, right? If I have a ruby laser or an argon laser, I know what that wavelength is. So now to get only one mode, my design parameter will be this, right here. This is what I designed for, the radius. What radius or twice that diameter do I make my cord so I only achieve one mode of operation. You with me? And that's what you designed for 8. Now I gave you some problems, and they had the typical nomenclature for how they have fiber. Like, it's like 100/200 fiber. Do you all remember seeing that in the problems? Did you have any questions at it? Post the solutions. It's just the designations. You don't have to worry about this. If I give you a problem, and I will, after I speak today, I will ask you to, what would the radius be to allow only one mode, right? Now, the question is, you want to make it just a little bigger than that. Not exactly that, because there's always some fudge whenever you do designs. You're going to get you're going to get a distribution of widths and stuff like that. So you make it a little bigger than that, maybe 2-3% bigger when you actually draw the die on this. But this is what you design for one mode. That's called single mode fiber using a graded, or using a step index. Most common things. Does anybody have any experience with this? By the way, most of the people that do design work with fiber optic cables are materials engineers. And you can easily step in that thing from here. If you work for IBM or Dow Corning or DuPont, anybody that's involved with fiber optic cabling and making devices to work with them seamlessly, then you will need a lot of material science background, because glass itself is something that they have to work with, and they have to make it somewhat malleable. They have to be able to flex the glass without shattering it. So they do a whole lot of stuff that I am not. I had when I did my master's doctorate, I started out in VLSI design, solid state physics, in electrical engineering. So it's under the College of Engineering, but did a ton of stuff with material science, physics, crystal chemistry, and all that stuff. There's a whole world that you're not exposed to. Crystal chemistry and all these things are all based on electromagnetic properties. And a guy named Linus Pauling, who was a 2-time Nobel Prize winner, actually wrote a book, The Nature of the Chemical Bond. It's all electrostatic attraction and repulsion. It's the reason chemistry works, but you're never told that when you have chemistry. You memorize all sorts of stuff. All right? It's a perfect electromagnetics problem for a statics problem, all the chemistry. But the thing is, when you have stiff crystals, brittle crystals, you can only bend those electrical bonds a slight amount before they shear, go into another state. And so with glass, they're always experimenting on adding things, doing things in the processing so they can bend it without breaking it. And it's not a trivial matter. If you're interested in that, I encourage you to pursue it in graduate school. There's a world of things you can get involved in. I tell you right now. There's all sorts of people interested in this. After class, I want to talk to you about your gigahertz thing. I mean, you told me you had a gigahertz bandwidth for a while.
Oh, yeah. Sure.
Anyway, that's fiber, what he's got access to. Now, NF is fiber, NC is clad. Let me show you one other thing before I leave this. This is step index. Here's what it really means to you. And you don't need to know more. I'm not going to test you on this, but this is in the real world. If you go and you're an engineer and you've got to interact with people who are talking about fiber optics. Well, they talk about the O mode. What they're really talking about, that this is the magnitude of the electric field versus radial distance. They're talking about something that is 0 and then it goes up and down, and this is about lambda over 2. It's very similar to that of free space. Rectangular guy. It's about, not quite. If you look at this equation right here, just think about this. If you set this whole thing, this radius here equal to lambda naught over 2, right? You cancel the lambdas, the 2's cancel. I got pi over k naught. Pi is about 3.14. K naught is about 2.45. This will be a little bigger. I mean, what it'll do is adjust this parameter for that, but it's about that. So keep that in mind as far as the physics go. Just so if you take a look at fiber, just say, you're looking at a project that you use a leftover project, you're an incoming engineer, you're trying to figure out what's going on. Take a look at the core of the fiber, get the radius, double it, that's about a half wavelength. And that'll give you enough, that's the information you need to know to figure out what laser was driving that. If it's ruby, it's one thing. Argon, I forgot all the laser types, but they're one of many lasers. I don't even know what gas FET's put out there. Each laser has a very selective line. Yeah.
As a fiber optic, always use a cylindrical Pardon the underneath.
Always. Oh, well, I say that to my knowledge, everything is cylindrical and it's in the O mode. Now, if you get anything with an elliptical surface to it, there's always an ellipticity because you never get a perfect circle. You just don't. There's some, but anytime you get that, the mode pattern on that is much, depends on the amount of ellipsis, but it's different. And not only that, it doesn't add to the amount of information transferred. There's no reason for it. Okay, there's one other thing I want to tell you about, just for your information. I'm not going to grade you on anything like this. This is step index, it's the most popular. There's also a graded index fiber, and it's called grid. In the book, he discusses it. That means there's not a hard transition from one index of refraction to another. What they'll have is a gradual change around here where it goes from the hard one to the soft one. Graded index fiber is something I don't have a lot of experience with, but to my understanding, it will allow more modes to travel down there if it's a short-range packet type of information. It's cheaper too, I think. I got it graded. When you have step index, it's harder to make, I believe, unless they've come up with something. Graded is easier because it is gradually changing its properties, not abruptly. So it's easier to make. And graded index fiber is something that is used, it's cheaper, to the best of my knowledge. I'm saying this because right now, there may be things that I'm unaware of. If somebody Googles it, you'll find out just Google fiber optic technology latest, and they'll tell you if you're interested in it. I'm going to tell you one other thing about this Bessel function stuff. In our waveguides in this class, we don't cover cylindrical. If it was up to me, we would. Cylindrical waveguides are used. They are. But primarily, most of the stuff that you're going to be dealing with any kind of microwave dishes, and if you take a look at the link to your, if you have a dish antenna on your roof or anything like that, it's a rectangular piece that fits in there, and it feeds usually from a coax. All right, usually rectangular guides are the ones you need to know about. All right, there are reasons to use cylindrical waveguides, but that's a little bit outside the realm of what we're going to deal with here. It's more graduate material. I can tell you about it if you're interested. It's easy for you to figure that out once you've been introduced to rectangular. How many co-op in here? All right, and anybody co-op in an industry that does any type of antenna engineering, microwave engineering, radar work, anything like that?
I worked at a defense company up in Huntsville.
At what?
I worked at a defense company in Huntsville.
Were you involved with any kind of antenna work, field work, or anything like
Probably.
that? All the stuff that you saw in the microwave range is probably rectangular guides, I'm guessing. And same with cell phone towers. Now, if you work in specialty areas, for instance, at plasma stuff, high energy physics, things where you're dealing with maybe a whole lot of information over one band or over two bands, you may see cylindrical, but it's rare. Just telling you. Okay. That's all you need to know about this. I'm going to give you 2 or 3 more problems that I'll create to ask you questions about this with solutions so you can assure yourself you know what you're doing, okay? Remember this. This right here is the key design parameter for single mode, and let me get to this. This is the number of modes. Now, why do you need the number of modes? If you're sending a packet of information, remember, the more the number of modes, the greater the actual, and we don't have the formulas for this in the book, the rate of dispersion of the pulse. Right? The faster it broadens, so you can't use it very far. The number of modes here, I don't really know of a real super reason for that, but it's an estimate of how to get it. I don't use this for anything. I use this for something. That's one thing at least I want to be aware of. And I'm telling you practically speaking. But there may be a great use for it. That ends chapter 7. I'm not going to ask you about the fiber communication systems for one big reason, because unless I can go into the device physics that drives these things, have you had your analog design class for FET as well as BJTs? Have you all or not? You know what a BJT amplifier is? You know NMOS technology, CMOS, PMOS, things like that. Well, I could go through it, but fundamentally, when you're talking about optical systems, you're talking about lasing. So you have a laser. It's actually, you're going to pulse. You're going to turn off and on a laser with the GaAsP, gallium arsenide FET, or some fast switching device. You're just going to turn it on and off. When it turns on, it emits light at that frequency, at a certain intensity. That's going to go into the fiber and be translated. And something I'll just mention to you, and it's because it's necessary to know. I put that up there, and that was something called the numerical aperture. Do you remember seeing that? How many do? It's called NA. Numerical apertures is one other thing you need to know. Those two things, but numerical aperture. Sorry, I didn't mention that first. The symbol is NA. Numerical aperture really is found, and I put the proof up on the board. I'm going to show you what it is, and I'm going to show you the formula that ultimately it ends up. Now, do y'all remember me doing that? I mean, did you take a look at the notes? Let me just recap. So when you talk about numerical aperture, this is the fiber. Right there, this is the cladding. And what we do is a little ray tracing. We say we have light coming in here and no light going there, and we call this the critical angle right there. Just showing you what it is. It's a recap. This is the direction the light's flowing. That's the critical angle. We have another angle here. And that angle is 90 degrees minus the critical angle. And then we have an angle here. And this I'll call alpha. So, this has to do with light gathered. This is our fiber. It's big. There's the core. And here's where I got a light source. Now follow me on this, because this will make sense. What this says is if this angle here is any steeper than this angle that's going to be associated with the critical angle after you do the ray tracing, then I'll have an angle here that will be greater than the critical angle, all right? I'm sorry, less than the critical angle, my bad, less than the critical angle, and some of the light will get into the cladding and it will cause that wave to dissipate. You follow me? So what the critical angle is the angle at which all the light has to strike. This angle or greater than that, in order to get the wave to propagate, we'll get a perfect reflection at the interface. That's the whole idea. Got it, everyone? So that's why I use this. If this is the critical, this is 90 minus the critical angle. And I can figure this out by simply using Snell's law, can't I? I just put down the relative laws. So if I have a critical angle here, and let's just say this is N cladding here, I'll call it NCL, and the fiber cladding is NF. All right. So I'll put the numerical aperture down in a second. I'll do this over here because I got a nice whiteboard over here. So now I'm going to say, what is the critical angle? Well, if I take the index of refraction in the fiber, right here, times the sine of the critical angle, this is Snell's law, then it would be equal to N in the cladding, right, times the sine of theta in the cladding. Now, what do you know if it's critical angle? What is this value? Well, it's 90 degrees, right? All right, so that means the sine here is 1, correct, class? Y'all follow me on this? This is the critical angle and how to get it. So if that's 1, there you go. That means the critical angle here is equal to really of the cladding, I'm calling it CL, divided by N of the fiber. That's the critical angle. Now, I come down here and I see that, well, just take a look at this. If I take this angle here as sine of this angle, just follow me, isn't that the same thing as cosine of that angle? I want to just follow me on this. Y'all follow me? The sine, because this is a right triangle, so the sine of this angle, which would be what? Opposite over hypotenuse, would be the cosine of this angle, which would be adjacent over hypotenuse. Does everybody follow the thought? So this angle, maybe you want to call this, I call it 90 minus that. I'll just call it, let it be. So I can say the sine of the critical is equal to cosine of angle B here. Agreed with that? I'm just showing you the process quickly. Next thing what I'm going to do is say if I square this, I get cosine squared of that, of angle B, is equal to NCL squared over NF squared. I'm just squaring both sides of that. And I know cosine squared of angle B right here. If I take a look at that, I'm not sure if this is the easiest way to do it, but I'll just show you so. And I know this relationship's true. This is going to be 1 minus the sine squared of theta B is equal to NCL over NF squared. And then I can go ahead and take that to this side, this to that side, and I can say sine squared of theta B is equal to 1 minus n cladding over NF squared. Just leave it at that. So I have that. Can everybody hear me okay?
Yes.
In the back, can you all hear? Now if I have this, I come back here. That's N fiber, this is N0. Typically it's equal to 1. We're talking usually about air. Usually. So now I come down here and I'm going to use Snell's law again right here. Now remember what Snell's law says, if we're assuming we have a dielectric that's lossless, it's really the index of refraction on one side times the sine of this angle is equal to the index, index of refraction times sine of this angle is equal to index of refraction of that angle times the sine of that angle, correct? Now I could put down beta, but beta is omega times square root of mu epsilon. Ultimately the omegas cancel, the epsilons cancel, and you're left with just square root of epsilon relative 1 and 2, which is the index of refraction. So here what we actually get would be sine of alpha times eta 0, which is usually 1, would be equal to eta fiber, or n fiber, pardon me, times sine of theta b, right? You can see what I'm going to go for. That angle sine of theta b is the square root of this, isn't it? Y'all follow me? Can you see it okay? Yeah. So now I come here and I say that really, or I come over here, I say N0 times the sine of alpha is equal to NF, and now sine theta b right here is going to be square root of 1 minus, and this is going to be n cladding over NF squared. And now I divide by N0, or the index of refraction of free space. This is in the OneNote, by the way, the proof. And now I get this. I'm going to do one more thing to make the formula the same way it appears in the book. Now you can see this, if I have NF here, if I bring it inside, I got NF squared, don't I? Can you all see that? If I have NF, bring it inside, NF squared, well, you see the NF squared cancels, and you end up with this as the final equation. This is called the numerical aperture, NA. The reason it's important is the larger that value is, the better it is at gathering light, and the less alignment you have. Now here's a real problem. When you have a laser just shoots a little dot, you know? If there was no air, there'd be no dispersion. The radius of that dot would be the same a mile away or 100 miles away. There would be absolutely no dispersion of the beam. Are you with me? Because it's a coherent source. But there's a problem in microelectronics, it's alignment. If you're putting together a system, you want a big numerical aperture, so if there's vibration or if there's a misalignment of the source to the fiber, it'll still couple. Do you all see what I'm talking about? So the numerical aperture tells you at what angle you have to be at. I mean, what's the maximum mismatch? This can be up, I mean, if you get 5 degrees, you're doing well. All right, but you would like it to be 90, it's never going to be 90. So you get a numerical aperture as sort of a figure of merit of how much alignment is needed in order to get that light to go down there. You all follow me? Now, how do you increase the numerical aperture? It's obvious. Get the largest difference possible between the fiber and the core. Are you with me on this, class? So if the fiber was 100 and the core, that's an exaggeration, I'll never get that, and the core was 1, that thing would be taking light from 86 degrees and still getting through. You all with me? And that's really it. I may ask you to calculate this. Would I give you this formula? Sure, I'll give you that one. I'll give you this one for, I erased it, number of modes. And of course I'd give you the one for single mode. But again, I don't test on that because this is really just an overview to make you aware. It's not to cause you to do design of fiber optic materials like it will be for some antennas and stuff. So that's the whole 9 yards of fiber optics and optical and dielectric waveguides. I don't worry about dielectric waveguides too much. They're just a couple of mirrors. That's all a dielectric waveguide is. It's a couple mirrored surfaces stacked, and you just figure out the cutoff frequency for a single mode is you get a half wavelength between them, just like a rectangle. That's it. And they should, I mean, Whitworth's book's got a lot of information about the mini modes and stuff. You don't need to worry about it. That's my opinion. Okay, now, are there any questions before I move on to antennas? This will be interesting at all. Are you with me so far? Yeah.
You said number of modes. Is that the same as like, 1, 0?
Yeah,
that's
it's
how
the number of modes, and if you want to know how they go, it's usually the 0 mode it's called. It's really a 1 mode. It's an 01. I mean 10. Then it's going to be after that, it'll be 11, then 20, but you don't have to worry about that for a circular guide. Actually, I'm not actually sure how the modes are ordered because I don't use them very often, but the modal pattern, yeah, you're right. It's how many different modes exist, which means how the wave is actually going to be, you might say the signature of the wave or the impression of the wave on the surface, how the contours are. And then the other, at a snapshot in time, the other thing it tells you is the velocity of each wave, but you don't need to worry about it. The more modes, the bigger the problem with velocities. All right, you get velocity dispersion. So now, is there any other questions? Yeah. Oh, you don't. I'm going to erase that, and I'm going to start with chapter 8. This is antennas. And I do this from a perspective, if I was sitting where you are, how would I want this information unwrapped in front of my face? I don't want to just start with a bunch of crazy equations because you want to appreciate it. I'm going to show you, and I'm going to show you why it's important and what it means. I always like talking to engineers because you have a natural kind of instinct that tells you what you need to know about a device. You always want to know some way of figuring out how good that device is. The term we use is figure of merit, or some figure of merit to tell us how well something's performed. I mean, as students, your figure of merit is your grade point average when you go for a job. That's a figure of merit, just telling you the truth. It's something like this for antennas, and the way we talk about it is gain. Now, let me just go through this from my perspective of what you would know. If we have an antenna, for now, I'm just going to say that's what an antenna looks like. An antenna can look like anything. It can be a parabolic dish. It can just be a flat plate that's in front of some sort of a conducting surface. It can be a thin wire. It can be a helix. An antenna can look like anything. This is just something representing an antenna. That's it. When you have an antenna, it's usually anchored to something, typically your house or the ground, or maybe an aircraft outer body, but it's something that actually interfaces with the atmosphere, all right, or free space, if it's deep space. It has to be something, it could be immersed into an anechoic chamber, but it's got to have some area in front of it, some volume where it can propagate radiation through. That's the thing. It doesn't do this, and you don't have truly an antenna in a cavity. Right? You do and you don't. That's actually called a probe. All right, what does an antenna do? Well, if you assume, for whatever reason, this antenna has a power source down there, and there's a total power going in there. That would be in watts, so you're going to have power. Now, just think about it logically. Power in, power out, right? We're going to assume all that power is launched as an electromagnetic energy. So if we go out a distance r away, and we made a spherical surface, that's not much of a spherical surface, but you can follow me. The area of that surface would be equal to what? 4 pi r squared would be the surface area, right? Of a sphere of radius r from that antenna. That's a lousy drawing, but I hope you can appreciate what I'm trying to do is show you some radial distance around that antenna. Now, if there was nothing to focus the electromagnetic energy, if I'm out a distance r away, I could say the average power density would be equal to the total power transmitted, which would be in watts, over 4 pi r squared. That should make perfect sense to you. Right? All that power, the further I go away, if it's evenly distributed, the less the power density. This would be in watts per meter squared. Makes sense to everybody? If you want sort of a visual aid, think of the sun. All right, if you're a distance, say the Earth away from the sun, it doesn't matter where you are. If you hold that radial distance from there, the power density coming at you from the sun is about the same. Or a candle, right? But it's not true with antennas. So if we have an antenna, we have something that focuses the electromagnetic power, and it's called the gain. Think of it this way. So the actual power density of this antenna has a gain, G, and that will be a function of angle. Now, the average power density, this is isotropic, by the way. Isotropic power or radiation. It simply means that it's distributed equally in all directions. If we have something where we have an antenna, then the average power density becomes this, transmitted power, over 4 pi r squared. But now it's times the gain of the antenna. And the gain of the antenna is an interesting thing. This tells you how it focuses power. It'll be a function of both the angle theta and the angle phi. Now, a logical question is, what is theta and phi? So, in general, when we're talking about electromagnetics, in the standard way we do business, we say, typically this is the x-axis, this is the y, and this is the z. This is for the coordinate transforms. And then if we come out a distance r away, right here, we talk about the angle theta measured from the vertical z-axis to the radial vector that goes to the point you're talking about out here. You with me on that, everyone? And this is going to be r vector. And we also take a look at an angle phi. And if you could shine a light down there and take a look at the shadow on the xy plane, this would be the angle phi. It's always measured, if you're looking down the z-axis, it's measured counterclockwise. Now, you all familiar with phi and you remember theta, don't you, class? There's coordinate transforms available. If you have r, if you want the z component, you take the cosine of theta times r, you get the z component of the point. If you want the x component, then you're going to take the sine of theta to get this distance, and then you'll take the sine of this, sine of that, or sorry, cosine of this angle to get x. And if you wanted y, it would be the sine of this angle. Sine of this angle times cosine of that angle times r to get y. But we could talk about this later. These are just coordinate transforms to get projections of the vector. Anyway, that's the standard way we do business when we talk about theta and phi. Now, I want to say one other thing. Usually when we're talking about antennas, they have a maximum gain in one direction, and that is termed the bore sight. It comes from a military term, a nautical term. If you remember in the day when you saw pirate movies and they had all these cannons on one side, right? Well, it's the bore sight of that firing power was perpendicular to the actual length of the body of the ship. That would be the bore sight, right? And when you're down the bore sight in an array antenna, it's called a broadside, which makes sense because it was called a broadside in military terms. And just to give you a heads up, a lot of these terms come from the military. So if you actually have an antenna where you have an array of antennas, but the gain you want is along the axis where the antennas lie, that's called an in-fire. Just some terminology that you'll be hearing and reading about. Now getting back to this is the average power density. And I want to make sure you see this from an antenna, right? If you know the gain, that's what it would be at a given distance. That's in watts per meter squared, right? You always assume an antenna works in the far field. Now, at least we're going to say far field. That means it's propagating electromagnetic energy. What I'm about to show you is important. So the question is, how do you get the electric field density out here from the antenna gain and the power transmitted? So if I'm out a distance R away, and I know the gain of the antenna, I have a power density in watts per meter squared, right? I'm assuming it's in the far field and it's radiating, correct, class? It's not near field where you have electrostatic and magnetostatic energy. Well, in the far field, what would the electric field be? Well, wouldn't it be 1/2 the magnitude of the electric field squared over eta? Would be the eta of free space? How many remember that? All right. If you don't worry about it, but this is the standard propagating wave's power density. It's always proportional to E field squared. It's multiplied by 1/2 because that E field would be the peak value of the E field. And it's divided by the intrinsic impedance of free space, okay? Which means if I know the transmitted power, the range, and the gain, I can get the E field, right? I set these two equal together. I get 2/8 over here. And I take the square and I have the E field magnitude. Do you all agree with that? Can I get the H field for a propagating wave? What is the ratio of E to H always if it's propagated? Magnitude of E, right, for a propagating wave over magnitude of H is equal to, what's the units of the E field? Volts per meter, units of eighths, amps per meter, right? Volt over amp is ohms, right? Ohms, intrinsic impedance of free space. So it would be the intrinsic impedance of the region actually you're propagating. Are you with me, class? Good on that? This is giving you enough information to appreciate a whole lot of stuff coming down the pipe at you. So what we would like to know for any device is this, right? We'd love to know the gain of any antenna. That tells us what we need to know. We can figure out from impedance matching how much power goes to that antenna, but we need the gain. So how do you get the gain? Well, first I have to expose you to things that have to do with the antenna's behavior. And some of you might know about this, but we get what's called a power pattern. Now, there's section 8.1 in this book, if you have there, you can turn there. On page 430 and 434, he has a few drawings, and I'm going to explain this the way I think it's appropriate so you don't spend a lot of time scratching your head about some terminology. When we talk about gain, we're really talking about the power and how the power is going to be dispersed in space. Now, Whitworth shows you things, and they're called power patterns, radiation patterns, I think he called it. The radiation pattern, he talks about the real radiation pattern normalized. Well, let me just make note of this. You all see this equation right here? I'm going to put it up there again. I'm going to say the average power density from an antenna is equal to transmitted power over 4 pi r squared. At a given range, that is a constant at a given distance r. But it's also multiplied the gain. And the gain is a function of both theta and phi. For an isotropic radiator, for something that has really no effective gain, it's 1, right? You all see that? It would be 1. It can't go less than 1 for its total average value, because that means less power is coming out of there than if you had an antenna. But the gain itself tells you how the power is really dispersed versus angle. Now, gain is really the same thing as how the power is dispersed. And Wentworth talks about normalized power, but gain is just as easy to understand, and usually it's done in dB, but it doesn't have to be. So what's typically done is, this is called a cut. They'll take a look at the gain of antenna, we're going to do it in linear, and they'll hold like phi at 90 degrees, and they'll take a look at it versus theta. So the gain may do this. If this is 0, it may do this. And this would be equal to, actually, let me do this. Let me call this 90 degrees and explain this. And this would be 0, and then this would be 180 degrees. Let me show you what I'm trying to do. If you think about a wire antenna like this, wire antenna of Wingfowl, we'll get there on this one. Well, that antenna, if I feed it right here with a voltage, plus or minus voltage, it'll develop a current I, like such. It'll have a current signature, but if I looked at how this thing radiates versus radial distance versus this angle, theta, call this the z-axis. This is for a wire antenna, it's well known. What you get is something like this. It would look like this. Right? And that's called, the max gain would be here. And this would be the power distribution. Do y'all follow me on this? So here it's versus angle theta, and the length of this vector r is proportional to the gain. So the gain's max out here. Do y'all follow me? So it's like a wiper arm, it's a variable length. Right up the axis of the antenna, it's got nothing, and it starts getting better and better and better. And when I'm coming out perpendicularly, it's going to be a maximum value. That's a typical kind of antenna pattern. Here I'm showing it versus spherical angle. Do y'all follow me on this? And it's a spherical type of thing. You might say the length of the arm is proportional to the gain at a given angle. Now, if we take that gain pattern and we sketch it this way, it would look something like this. Do y'all follow me? Here I'm just linear angle theta this way. And when you talk about this, you can see the angle would go from 0 to 180 degrees. You with me? If you went from 180 to 360, it would repeat itself. It would be periodic and from 0 to really 180 degrees. But that's just some insights that help us. Now, in Wentworth's book, what he does is show you the actual, he shows you drawings of the antenna pattern and he talks about some of the terminology. I want to mention some of the things now as far as terminology goes, because I'm going to get into this, but I need to give you enough background so I use a term it won't be completely foreign to you. Can you all appreciate this gain is really proportional to the antenna power pattern, right? Now I could normalize this, and I could take the gain pattern divided by the maximum gain, and this value would be 1. That's what he does in his book when he talks about normalized power. But gain and power pattern are interchangeable. Normalized means you just take the max value and divide it into everything so it's scaled. That's all it means. Nothing more. Now, when we talk about gain, one of the things you have to do is also appreciate what it really means to you and me. I try to give you an idea of that. But there's a few things that happen that are necessary outcomes. And the question that should be in mind, well, how do I calculate it for an antenna, right? And the way you have to do that is you have to find the electric field from that antenna as a function of angle. And then from there you get the power. Once you have the power, then you can get the gain. I'm going to show you how, okay? And I'm not trying to bore you with this, but I can imagine you want to see some hardcore work. And So another way of thinking about what I showed you here is that if we talk about gain, or G is the symbol, at any given angle, it's really the power density, the average power density with the antenna, divided by the average power density if you had an isotropic radiator. Now think about this. That's the real power density, the top one. If I divide by the isotropic, then I figure out how much better or worse it is. You with me on that? But there's one thing that's true. If this is the average isotropic power, right here, I'll just call it ISO. I can say that P average for the isotropic case is really equal to the total transmitted power, right, over 4 pi r squared. Do you agree with that? That would be the average power density, correct? Without spending a lot of time on the justification for this, for all the other calculations, we arbitrarily, or I arbitrarily set r equal to 1 meter. That way I can get rid of it. It doesn't matter how far away I am, so make it 1, because then it goes away. And it doesn't change anything. Are you with me? So now that's the average power density at 1 meter. You'll notice total power in there, right? So I come out here and now I say it's average power, whatever that is, divided by this, which is P total, over 4 pi. Right? And I just put the 4 pi down there because I transferred from up there. Now when I take this, I've got average power by P total in there. And here's what Wentworth does. He says, what I can do with average power is I can define it as P average itself will be equal to the normalized power pattern. He calls it Pn of theta and phi. All right, it's that times the maximum value of the power pattern. Just go with me on this. This is going to be a maximum value power pattern when R is 1. Normalized has a peak value of 1. Do you all follow me on this? I'm going to come to a conclusion in a second. So if I take that and I stick it in here, now I can see that this is going to be P max over P total divided by P normalized over pi, and then it's times 4 pi upstairs. All right, I got that. We'll stop here before, I don't want to say anything that's going to be too confusing. Oh, I got to say one other thing, because Wentworth doesn't use the term gain, he uses directivity, but let me just explain something. We talk about gain, that's the real thing you want. But what gain is equal to, and I'm going to put it over here. We'll come back to this. I just realized that he uses directivity. So gain itself, right here, is actually equal to something called the efficiency times the directivity. Now, D is the directivity. And what I'm calling EF is the efficiency of an antenna. So D and G, the directivity and gain, are proportional to one another, but the efficiency is the key. Typically, the efficiency is about 1. It's about perfectly efficient. It means when you design an antenna and you feed it, you get perfect, you don't have any kind of impedance mismatch. That's the whole idea. If there was an impedance mismatch, or if there was thermal heating, then the efficiency could go down. For now, just assume it's 1, and that means, at least for the purposes we're going to talk about, the directivity can be equal to approximately the gain. They are interchangeable if the efficiency is 1. But really, the efficiency is in this equation. I use gain and directivity interchangeably, because if you don't have an efficient antenna, why are we doing business? I made an inefficient antenna one time, and I really was sweating bullets on this one. And the guy that assembled it put a huge solder ball at the input from the coax, and a solder ball causes a huge impedance at gigahertz frequencies, and there was impedance mismatch there. Luckily, the guy that was at the test site uncovered this stuff and took a look and got rid of the solder ball and worked. But that's where efficiency can kill you. You have somebody assembling something that isn't you. I'm just about out of time, but I want to just write one thing down. So I didn't have time to get this in from a real antenna to show you. This is the one equation you're going to take. The directivity in general, you can find for any antenna by doing this. I didn't get to it. So write this down. The directivity itself as a function, well really, this is going to be D max, the maximum value, will be equal to 4 pi on top, and then it's going to be a double integral of the normalized power pattern, or gain pattern, that n is normalized. It's a function of theta and phi. Then you multiply this by sine theta. This has to do with the spherical coordinate integration, where normally it's sine of r squared sine theta d theta d phi is the surface, outer surface differential area. You don't have to worry about this. It's sine theta times d theta d phi. Here d phi goes from 0 to 2 pi. This is over the entire spherical surface. And theta goes from 0 to pi radians. This is the definition of D max. Pn theta phi is the normalized power. It's really normalized power. Radiated power. And it's just equal to the average power's maximum value over the actual average power, or average from an isotropic radiator, both with distance r equals 1. I gotta spend more time on that. I'm going to just ask you to read the stuff, and I'm going to give you some problems to do for Friday. The good question is, do we have a quiz Friday? It's a fair question, right? Answer is, it will be based on this homework, not the way you got stuff, and it will be something something related to that, all right? And I'm not going to do that. I'm not going to ask you a question on directivity, even though I'm going to have you calculate some. It would be related to this. Follow me, class? And I'll give you problems that are representative. Sorry I didn't get to where I was going, wanted to go, but I hope you appreciate it. Now, if you want the other assignment you turned in, come upstairs. I've got it up there. I'm sorry I didn't break it down. Okay? Just come on. It's on the 4th floor. My office is 430. Any questions? Did everybody pick up their stuff? Some people walked in. I don't think you did. Tom, did you do your homework? Tyler, are you Tyler? Yes, sir. Tyler, come on. And